Good day, ma'am, and listeners. Today we will be reporting about our topic entitled Termite Inspired Buildings. It's presented by Tenedero Carl, Dilly Dilly Zay, De Leon Jason, and Bravo Anthony. To start off, we'll head to the principle. So, for the introduction, effective use of natural ventilation is a viable strategy to achieve energy efficient buildings. But this strategy is difficult to master because the air intake and discharge may be more or less than what is really needed. So, the essence of this energy efficient buildings is that it is the adaptability of termite mounds with their environment throughout different seasons, which is achieved with the minimum energy consumption through what we call the natural ventilation, which is basically the main principle of the termite-inspired buildings. And it only accounts of good architectural design of structure. So we head to the stages of ventilation, namely as the three main stages: draw, passage, and exhaust. Wherein draw, it means draw of fresh air, wherein it also includes wind, and not only wind but also groundwater. Later it will be discussed. And for the passage, it's passage of air through the interior spaces of the termite mound, where it includes the complex structure of the mound and also the metabolism of the organisms, specifically the termites inside the mound. And lastly is the outlet or the exhaust of air. So as a breakdown, the first is draw of fresh air through wind, wherein the inflow of air into the mound is mainly facilitated by the wind. However, there is an uncertainty on the likelihood of wind direction and wind speed in a certain opening. Therefore, the inflow of air into the mound is not reliable on the direction and the speed of the wind towards a certain opening. So, in order to create the airflow within the mound, termites strategize on height difference between 2 points, namely the inlet and the outlet points, as shown in the figure, wherein the inlet points is the lower portion of the mound and the outlet point is the upper portion of the mound. The principle behind the height difference causing the airflow is the Venturi effect, in which a low velocity leads to a high pressure and vice versa. It is inferred that the wind velocity increases with height, making the topmost portion of the mound having high velocity wind coinciding with low pressure. So in this figure specifically, the top portion where the chimney lies creates a negative pressure that cause a suction force inducing an upward airflow from the nest to the chimney. So second is draw of fresh air in groundwater. So water is also a tool for maintaining cool temperatures inside the mound when the air flows during extreme heat conditions. Termites require great amount of water to maintain their metabolism. They also use water as mortar for their nest on consumption. That's why termites usually build their nest near an aquifer, wherein aquifer are soil layers that is permeable enough for groundwater to flow. Termites usually build their mounds, near aquifers for water supply. So during extreme heat conditions, they move wet soils taken near the aquifer to be placed in the mouth of the air inlets to achieve what we call evaporative cooling. So this evaporative cooling occurs when inflowing hot air from external environment is in contact with water, which will wet the air and cool the entire nest. So not only the air but also groundwater plays an important role for drawing fresh air inside the nest. So the second stage is the passage of the air through interior spaces. As you can see in the figure, there is this complex structure of the termite mound. The morphological features and interconnection of the channels inside the mound allows air to circulate through the entire mound. The channels in the mound is categorized into three networks. The first network is located around the main nest, where large diameter underground tunnels spun around the nest and is connected by series of sub-channels. The second network is the connection of the upper tunnels that connects the lower section of the upper chimney. And lastly, the third network is the surface tunnels around the mound which are connected to the first and second network. So also considering inside this mound, there's what we call the metabolism of organisms. The fermentation of fungus, combs, which are the food source of termites, produces heat and warms the nest. The significant population of termites also contributes to heat. Then hot air produced goes up and flows across the walls, taking note that the porous layers of interior and exterior surfaces allows the exchange of oxygen and carbon dioxide. Lastly is the exhaust of air. So the variation in temperature is the primary cause of heat transfer within the mound. It will lead to total air density differences in natural heat transfer. So hot air goes up and exits through the chimney, and cool air inflow starts at the nest of the mound, taking note of the suction force due to negative pressure in the mound, which contributes to the airflow.
So now you know the principles of the ventilation system of a termite mound. Now, we move on to the application of the system to buildings. I am Anthony Renzo A. Bravo. I'll be discussing to you the application of the system to Eastgate Center, one of the iconic inspired buildings of termite mound. Eastgate Center is located in Harare, Zimbabwe. It opened in 1996. Mick Pierce, the lead architect of the project, drew his inspiration from the remarkable mound building termites of South Africa. He modeled the self-cooling system of the building to the mounds of Macrothermes michelseni and Macrothermes subhyalinus. To the left is an example of the mound of Macrothermes michelseni, and to the right is an example for Macrothermes subhyalinus. Termite mounds are structurally diverse. Eastgate Center melded many of these diverse features into a single functional building. Two models of mound ventilation were used in this building. The first one is thermosiphon flow. This was modeled by Martin Luscher. What happens here is that heat from the colony, roughly 100 watts, imparts sufficient buoyancy to the nest air to loft it up into the mound and drive it to the porous surface. Then, the air gets refreshed as heat, water vapor, and respiratory gases exchange with the atmosphere across the porous walls. Then, this refreshed air, having higher density, moves downward into open spaces below the nest and eventually through the nest again. This mechanism is thought to operate in mounds with capped chimneys such as those of Macrothermes michelseni. The second one is induced flow, better known to engineers as stack effect. In here, the large chimney vent exposed to higher wind velocities than are openings close to the ground. Through venturi flow, fresh air is drawn to the mound through the ground level openings, then through the nest and finally out of the chimney. Contrary to thermosiphon, which has a circulatory flow, induced flow is unidirectional. This mechanism is thought to occur in open chimney mounds such as those of Macrothermes subhyalinus. So how are these models implemented in Eastgate Center? For induced flow model is evident in the row of stall stacks that open into voluminous air spaces that permeate through the building. While for thermosiphon, heat from the building's occupant machinery as well as stored heat in the building's thermal mass help drive a thermosiphon flow from offices and shops upward toward the rooftop stacks. In the climate of Harare, the combination provides for an impressive steadiness of interior temperature without resorting to a costly energy-hungry air conditioning plant. To give you a clearer idea on how the ventilation works in the building, here's what happens. First, air is continuously drawn from the open space between the two buildings by fans on the first floor. Remember that these open spaces are covered by glass and open to the local breeze. Then, the air is pushed up to the vertical supply section of the ducts that are located in the central spine of each of the two buildings. Through this, fresh air enters into offices and replaces the stale air, which rises and exits through the exhaust ports in the ceilings of each floor. For reference, the red arrow in the picture represents represents the movement of the stale air, while the white arrows represent the flow of the fresh air. Then ultimately, the stale air enters the exhaust section of the vertical ducts before it is flushed out of the buildings through the chimneys. Through this design, Eastgate centers cut 10% of the energy consumption compared to conventional buildings of its size. Moreover, Eastgate owners saved $3.5 million from not implementing an air conditioning system to the building. The design is also eco-efficient, and tenants also benefit. Their rents are 20% lower than those of occupants in the surrounding buildings.
Hello, I'm Jason De Leon, and I'm going to talk about the prevalence of the design and how many years has it been applied. So in 1991, an investment group in Harare, Zimbabwe, hired architect Mick Pierce to design a building without the need for air conditioning expenses. He then had the idea of using biomimicry and came up with a self-cooling termite mound-inspired design. The building was designed from April 1991 to December 1992. Construction started in 1993 and was finished in 1996. The building was also opened in 1996. Now, the second building is the Council House 2, located in Melbourne, Australia. It was also designed by architect Mick Pierce. Construction started in 2004 and was finished in 2006. Council House 2 was also opened in 2006. As of today, there are only 2 termite-inspired buildings in the world, which are both designed by the architect Mick Pierce.
Good day everyone. I am Aaron Zay F. Dilidili and I will discuss about the advantages and disadvantages of the termite-inspired structure. Advantages: economically good, since the energy consumption is reduced due to the fact that there is no air conditioning system installed. There is lesser electricity payment for the building itself. Thus, it saves money for the company. Also added to this, maintenance of the cooling system, which comprises of the ventilation fans, will not be costly. Because of these things, the tenants who are occupying the building, such as shops and store owners, have 20% lower pay rents in Eastgate. The company saves 3.5 million for a 36 million building. The second advantage is less energy consumption. The Eastgate consumes 35% less total energy than the average consumption of 6 other conventional buildings of its same size with full heating, ventilation, and air conditioning system installed. Also, it uses less than 50% energy annually compared to a conventional building of its size. While Council House 2 in Melbourne, Australia has 80% reduction in typical energy use and 70% reduction in water use. The next advantage we're talking about is pollution emitted is lessened. Without air conditioning and heating system installed for both buildings, there is less emission of harmful gases such as CFC and CO2, making the buildings environmental friendly. Next is sustainable structure. The Eastgate and Council House 2 are built in a way that they are less costly and expensive to the people without disregarding the quality of the building itself. These 2 buildings stand up to this day until the next generations to come. The last advantage we will talking about is self-cooling mechanism. The 2 buildings have a self-cooling mechanism of its own. It is able to warm itself at night and reduce heat at day. Now, we will talk about the disadvantages of this kind of structures. The one and only disadvantage of this structure, termite-inspired building, is although the design is good, the building or construction of the structure itself is challenging. Building this kind of structures requires a lot of thinking to be made. There are a lot of conditions to be fulfilled so that you have a building that can cool and warm itself. Due to the complex design of the termite mound inspired building, the structure cannot be copied easily. The principle may be the same for the two buildings, Eastgate and Council House 2, but there is a lot of adjustment so that the structures will be sustainable and is high quality. Finally, to end the report, the architect Mirkpis continues to develop the design of the termite mound. The architect Mirkpis himself described the buildings as somewhat a building attaining life of its own.